we are now going to talk about the derivative. So the derivative is one of two main concepts in calculus. You have the derivative and you have the integral. And what we're going to see near the end of the course is that these two are actually inverse operations of one another. So doing the integral is like doing the derivative backwards, and vice versa. So the derivative can be thought of as the instantaneous rate of change of a function. And we really introduced this idea at the beginning of when we talked about limits, and we were talking about the average rate of change of a function and how you can make that interval shrink down to 0. And when you do, you get the instantaneous rate of change of the function. And that's actually the idea of a derivative. So just real quick review. If you remember, if we have like some function y equals f of x, and we have a point on this function x and another point x plus h, right? There's these two ordered pairs, so this is x plus h, f of x plus h, and then this is x, f of x. Okay, then the slope of the line through those 2 points is the average rate of change of the function. Okay, and you could write this. This was the difference quotient, right? You could write it as f of, so it's the difference in the y values, so f of x plus h minus f of x over the difference in the the x values, that would be x plus h minus x. And then we saw you can reduce this by canceling the x out in the bottom. So you have f of x plus h minus f of x all over h here. And so h is basically the width of the interval, right, that you're taking the average over. So that's equal to h here. And the idea is if you let h go to 0, then x plus h is going to travel over to x. So this dot will travel down the curve. And the slope of the line going through those 2 points is going to get closer and closer to the slope of the tangent line. And what I've done here is I printed this out as an example. And you can see here, in this case, the curve is kind of concave down, and this is the point that we're interested in. And this is this line L here, that's the tangent line of the curve at that point. Okay, so if this is x plus h, then this is the average rate of change going between the, in this case, x naught and x naught plus h. And then as you let h get smaller and smaller, so h is going closer and closer to 0, which means this point is going closer and closer to p. So this, you can imagine it traveling up the curve and stopping and then taking another average rate of change and another average rate of change, another average rate of change. You can see that the slope of these lines, and these are called secant lines, the slope of those lines is approaching the slope of the tangent line. And so as the limit as h goes to 0 is actually equal to the slope of the tangent line, which is the instantaneous rate of change of the function. Okay? And so you can define the derivative here as the limit of this difference quotient here as h goes to 0. Okay? So the derivative of y equals f of x, I'll just write this, and I want to check and make sure, see if there's any conditions. I didn't look here. usually this one is pretty general, so I have it right here. The derivative of a function f of x with respect to x. No. There's no condition except that the limit has to exist. Okay? It's given as follows. So you would do f prime of x. So that this is, there's going to be, we're going to see that there's different notations for the derivative. Okay? And this to me is kind of the easiest, but we'll look at some other notations. So f of x is the function, f prime of x is the derivative, and it is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay? So let me do an example of this, and I'll do one that I haven't done. So I've simplified some difference quotients in an earlier video when we talked about the average rate of change of functions. And I did like a quadratic equation, I did a square root function, I did inverse, a 1 over x function. And you might want to go back and look at those. I'm going to try to show, some of these as we go through these videos here, but you might want to go back and look at those. What I want to do here is I want to do just the following function. So f of x is equal to x cubed. So we haven't done x cubed yet. So I want to find f prime of x. And this is going to be the limit as h goes to 0 of, I'm going to put x plus h into x cubed. So it would be x plus h cubed minus just f of x, which is x cubed all over h. So it would look like that. So now what I need to do is I need to expand this out. So this is like taking x plus h times x plus h times x plus h. And you could FOIL 2 together, and then you could FOIL this together with a trinomial. Maybe I'll actually do that up here for you. So if I FOIL the top two together, that'd be x squared plus 2xh plus h squared. And I'm going to multiply that by x plus h. Okay? And now what I'm going to do is I'm going to take x times all this and h times all that. So this would be x times x squared plus 2xh plus h squared. And then plus, so it's like I'm taking this whole thing and distributing it over the x and over the h. X squared plus 2xh plus h squared. Okay? And then I'm going to distribute the x over that and then the h over that. And maybe what I'll do is I'll do that right down here. So the limit as h goes to 0. And so I would get like x cubed plus 2x squared h plus xh squared. And then this would be plus x squared h plus 2xh squared plus h cubed. All this minus x cubed all over h. Okay? And then these you can actually combine. You get x cubed, and then you're going to get 3 of these, this plus this, so 3x squared h, plus, and then you're going to get 3 of these, with the h squareds in there. And then you have an h cubed minus x squared all over h. And I forgot to put this limit as h goes to 0. Okay. And now let me also say that there's a way of expanding this out. I could have went directly from here to here using the binomial expansion theorem. You can check a video. Just type out binomial expansion theorem into YouTube, and you can find a video on how to do that if you're interested. Otherwise, you would be doing you'd have to FOIL a bunch here to do that. Okay? And so now the x, and this is x cubed, not x squared, there. The x cubes cancel out, so I'm left only with things that have h's in them, right? 3x squared h plus 3xh squared plus h cubed all over h. And then you could factor an h out and cancel it, and you would just be left with the limit as h goes to 0 of 3x squared plus 3xh plus h squared. Okay? And then, now you can take the limit. It's just no problem here. You can just, both of these terms are going to go to 0, and you'll just be left with 3x squared as your derivative. So the derivative of x cubed is 3x squared. And if you've done any calculus or seen anything, you know that there's a power rule that says you can bring the exponent down in front and then subtract 1. That's actually what happened here. We brought the 3 down and subtracted 1 and got a squared up there. Okay? So this is kind of a proof that that works for x cubed. Now this is the derivative function. If I wanted to find like the derivative at a certain point, like at x equals 5, let's say, f prime of 5, well, if this is the derivative, then I just have to plug in 5 here. I'd get 75. So the slope of the line so you have this curve, right? And at 5 here, wherever it is, the slope of this line is actually 75. Okay? So this is actually a function that will give you the slope of the curve of the y equals x cubed curve at any point, and you just plug in wherever you want to find the slope, and then you get the slope of the line at that point. Okay? Now this is actually the way that I prefer to do it. I think this is just makes more sense to me, simplifying, getting this, and then I got a function where I can find any slope, right, for any x value, and I like that. That's just the way I like to do it. Now the way that your book teaches this is it actually, in the very first section of the chapter, it teaches how to find the derivative at a point. And so kind of like a function can be continuous at a point. And if it's continuous at every point in its domain, then you would say the whole function is continuous. Well, a function can have a derivative at a point, and then if it has a derivative at every point, then you would say it's differentiable. And so really, in a sense, a derivative is kind of defined for each point in the domain, and the function is either differentiable or not. And if it's differentiable at all those points, then the entire function is differentiable. Okay? Now, in this case, we can see that for any x value, none of this depended on the x value. So you don't get any problems. And so this is actually differentiable. The y equals x cubed is differentiable at every point in the domain, because I can plug in any x value and I don't get a problem. But if I had like 1 over x squared or something like that, then it wouldn't be differentiable at 0 if this thing was 1 over x squared, because you couldn't put 0 in the denominator. Okay. So now what I want to do is let me at least show you the way that they define it at a point. Okay. The derivative of y equals f of x at point we'll say x equals a, or something like that. That's good. And then the way that they define this would be the derivative at a, and then I would plug in a there. And this would be the limit as h goes to 0. And now what I'm going to do is I'm going to plug in, instead of x plus h, I'm going to plug in a plus h, like this. Because I'm not leaving my x open. It's not any x, it's at x equals a. And then instead of f of x, I'm going to have f of a, and then all of this over h. And so this is how they would define the derivative at a point. Okay? And so let me go ahead and do an example of this. Let's say f of x was equal to, we'll say x, the square root of x minus 1. And we want to find the derivative. We want to do this at x equals 5, let's say. So then I'm going to find the derivative at 5, and this would be the limit as x goes to h, and then I'm going to have 5 plus h. The square root, this will be the square root of 5 plus h. So instead of plugging in x plus h in here, and this is 5 plus h, and then I'll have a minus 1, actually. So instead of putting in x plus h into here, I'm putting in 5 plus h, okay? And then, instead of putting x here, instead of having f of x here, I'm going to have f of a, and that's going to be the square root of 5 minus 1, like that, and then all of this over h. So basically, instead of putting x plus h into the difference quotient here, I'm putting in a plus h. In this case, my a is 5. Okay, and then I can go ahead and find this derivative. So I'm going to multiply the top and bottom by this conjugate. This was the trick we learned last time. And I know that this here is just square root of 4, so I can do that. Okay, and so I'm going to multiply top and bottom, and when I multiply these here, it's like the sum and difference of a binomial, and so it'll be the difference of the two squares. So I'm going to get the limit as x goes to h, and then I'll have this whole thing squared, so 5 plus h minus 1. The square root of that squared just gets rid of the square root, and then this squared, so that would just be 4, all over h times 5 plus h minus 1 plus square root of 4. Okay. And then this would be the limit as x goes to h. Now these become 4, and then it cancels out there, so I have just an h on top, and then an h times all that on bottom. And now I can cancel out that h, and I get limit as x goes to h of 1 over the square root of 5 plus h minus 1 plus the square root of 4. And now I can let my h go to 0, and then I just get a 5 minus 1 here. Right? So when I take the limit, I would get the square root of 4 plus the square root of 4. And so now this would be like 2 square root of 4. And the square root of 4 is just 2, so this would just be 1/4. And so you see what I get is an actual number. So when I take the derivative at a point, excuse me, I get the actual value of the slope of the line at that point. So I don't get a function, I get an actual value. So if I would have just taken this, what I would have gotten here was 1 over 2 times the square root of x minus 1. This is actually what I would have gotten, and then see, you put in 5 here, and then you would get the 1/4. Okay? So I just think this is nicer. I think it's a little easier just to do it in general, and then you can plug in any point, and there's a lot of benefits to doing that. There's a lot of problems that you can solve, like you might want to find when the derivative is equal to a certain value. Oftentimes we want to find when the derivative is 0, because you got a horizontal tangent line, and as we're going to see, that's when a graph changes direction, where it has maximum and minimum values. Okay, so let me show you then just a little bit of notation here. So you kind of see this, okay, and then whatever function, if this were g of x, this would be g prime of, this is f of x, f prime of 5. If this were g of x, it would be g prime of 5, right? Or g prime of x, okay? But here is some other notation. This is, and I'll move this, and we'll use this as an example. So let's say we have f of x is equal to, let's say, x minus 1. Okay. We could also think of that as y is equal to the square root of x minus 1. And so, this is like f prime of x is equal to 1 over 2 x minus 1. That's what it would be. Or we could do f prime of 5, and that's just equal to 1/4, right? But another notation here is if this is y, and we know that, then I could say dy dx is equal to the derivative. And it would look like that, dy dx. So this is kind of like this is almost like an infinitesimal small interval, and this is that infinitesimally small distance that it travels. And the idea is you're taking these two really infinitesimally small quantities, and you're finding the ratio, and you're using that then as the instantaneous rate of change. Okay, now it couldn't be at that instant, because then you'd have 0 over 0 here. But the d is like, it's called a differential. The differential of y divided by the differential of x. Kind of like when we take the slope of a line here, right? We say it's the difference in y values over the difference in x values. Well, the derivative is like the differential of the y, the infinitely small difference in the y at that point, and the infinitely small difference in the x at that point, and you get the derivative. Now, of course, that's how they originally thought of it. That's how the two people that came up with calculus is Newton and Leibniz, and they were two different mathematicians, and they came up with it independently. There was a big controversy about who was the real inventor, but really, when people go back and look at the history, it's pretty clear that they both came up with it at the same time. So it's kind of like history was ready for these ideas. And they actually thought of them as infinitely small values, even though technically with real numbers they said it was an infinitesimal was smaller than every real number but bigger than 0, an infinitely small value. And as we know, there is no number that's the smallest real number that's still greater than 0, because you can always go closer and closer and closer to 0. But that's how they thought of it. They knew that it wasn't logical, but it worked, and people understood that it worked, and later on then it was defined in terms of limits. Okay, so oftentimes this notation is the sort of notation that Isaac Newton is credited with. This is the sort of notation that Leibniz is credited with. Okay. Now, if I wanted to do this at a point, like at 5, what I could do is I could say like dy over dx at x equals 5. So I draw a line and I say x equals 5, and that's 1/4. Okay. Another thing I could do is I could say d dx of the square root of x minus 1. So here I'm saying take the derivative of what's in the parentheses with respect to x. It's always, the bottom is with respect to what variable you take the derivative with. Okay? And so then this would be, 1/2 square root of x minus 1. And you could do, let me leave it like that. Another thing is if you have this and you didn't use function notation, sometimes they just do y prime is equal to 1/2 square root of x minus 1. Okay? So they might just use y prime instead of f prime of x. Okay? But these are the kind of the most common. And I like this notation, especially when we do the chain rule. I find that this helps break the problem down. And we're going to see this later on when we do the shortcut rules. Okay, and this notation is really easy to use, but this notation is pretty helpful. One other thing is, let's say you have something else. Let's say you have, I'm told that s is equal to the square root of t minus 1. Let's say that's what I'm told. Then I could say that ds with respect to t is equal to 1/2 square root of t minus 1. So it depends on, this is the function value, and it doesn't have to be y and x. It could be some other variables. But this is how you would use that notation. Okay? And so you'll get good at using these notation in different situations. Let me actually state that there's actually one more type of notation, and it's this notation. This is the least used, and I don't use it very much at all. But it would look like this. They kind of say this is when you use the derivative as an operator. This is saying take the derivative with respect to x of this function inside the parentheses, and you get 1/2 square root of x minus 1. So that's a different sort of notation. But these are kind of the most common notation. So just be on the lookout for that. Get used to whatever notation they throw out at you. And they will throw out different notation at you.